Okay, in the final phase of work on the gridded hybrid model, we're going to be modifying this model to remedy some deficiencies associated with it. So you may remember that if we run this model now, we will see some diversity over time, reflecting the different number of individuals who begin in different patches over time. We have some variability here in the original number of individuals who are in different states. But over time, if we run that model, it all sort of washes out. This washout is despite the fact that we have a diffusion coefficient that does vary, so there's different rates of diffusion into a given patch, but eventually with enough time the patches all become uniform, because given enough time, diffusion coefficient, these creatures that we're simulating will make a patch overcome a couple extensions to this model. These extensions are going to fall into two basic categories, ladies and gentlemen. One of them is we are going to allow for differences in the birth rates associated with different populations. So we're going to, instead of having each patch which has a birth rate associated with it, be just using some global birth rate. We're instead going to have variability in the birth rate between patches. So the way we're going to start that, it's going to lead on to a different problem, which we're going to fix. We're going to take the birth rate from main. I went there and I cut it. Control X, or you can use edit cut, and I'm going to take that into patch, and ladies and gentlemen, I'm going to draw this in here in patch. Okay, and having done this, ladies and gentlemen, I am going to go and put in place a link from this birth rate to these births here, and we are going to go and further modify this formula such that it refers directly to the birth rate within this this class. So the local birth rate, which is going to be specific to a patch. Now, for main, ladies and gentlemen, we are going to have a birth rate which is going to be specified as some mean birth rate, and then, ladies and gentlemen, a standard deviation, the birth rate. We're going to assume a normal distribution with a fairly wide standard deviation. So going back to main, we're going to add two parameters to main. This will be mean, and for reasons we'll get to in a bit to save us work later, we're going to call it mean birth rate. Okay, and we'll call it birth rate standard deviation. Another parameter is going to be a birth rate deviation, ladies and gentlemen. This birth rate deviation is going to represent a deviation around that mean value. Okay, according to a truncated normal distribution. So this is going to be, we can call it standard deviation birth rate, like that. Okay, and the default value I'd like to assume for standard deviation birth rate is 0.05, and for mean birth rate, ladies and gentlemen, we're going to assume a default value of 0.1. Okay, next, in the patch, we're also going to take mortality rate, which has uncharacteristically been a dynamic variable. We're going to delete that, get rid of this link, and we're going to go to main, ladies and gentlemen, and we're going to insert into main a parameter here that's called mortality rate. And obviously we could make this different for the case of mature and immature individuals, but we will go and just impose an overall mortality rate. Now we're going to impose a mortality rate of 0.1, and accordingly in the deaths flow here in patch, we're going to refer not just to mortality rate but to main.mortality rate. Okay, now you'll notice something, which is right now this mean birth rate, it's the same value as the mortality rate. Both by default are 0.1. And that's really important, because if the system is out of balance, what will happen is if the birth rate is greater than mortality rate, what's going to happen is there's going to be migration, but you're going to have the system just filling up with organisms, because the birth rate is going to exceed the death rate. And they'll leak out, but unless those other cells have the opposite, you're going to have this kind of situation where you have this buildup. Similarly, if the birth rate is less than the death rate, you're going to have a drop down, potentially point of extinction. You're going to have some coming in from elsewhere, but unless they have something that balances that, you're going to have the system out of whack. And in general, it's going to be quite unlikely the system as a whole is perfectly balanced. So you're going to either have it filling up or dying off in terms of number of individuals if there's imposed variability. So we're going to go to patches here, and we're going to impose some variability in birth rates and death rates. But we're going to see that this causes some issues. So let's go to the population of patches. That's going to specify the birth rate for each path to use. By contrast, we're using a single death rate, which is specified here in main for the mortality rate. But the birth rate, we're going to have variability. It's going to be determined for each patch. That's why we put the birth rate in the patch. So let's go to patches, ladies and gentlemen. And for birth rate, we're going to use a normal distribution as our basic mechanism. Now, unfortunately, any law normal distribution, most regrettably, forces you to specify the sigma first and then the mean, which is the opposite of how we normally define it, use it, convention in statistics. But we'll accord with those requirements. So we're going to have a standard deviation birth rate, deviation birth rate, and then a mean birth rate. Okay. Ladies and gentlemen. Now, we could draw from this normal distribution, but there's a problem. The normal distribution has tails on both sides. It is symmetric by itself, and in principle, therefore, particularly if mean birth rate is small enough and standard deviation is large enough, it could be negative, which we definitely don't want. So we're going to put in a max of 0 in this value, which is basically going to keep it from going negative. If this gives something that's negative, the max between 0 and it will be 0. Okay, ladies and gentlemen. So we're going to go. I will actually, to be safe, I'm going to save this as another file here, and I'm going to build this. Okay. Okay. So we built it successfully. Let's go run this guy. Okay. And we're going to run this out. Okay. And again, we start with some variability, and this time this reflects. The early results reflect both the variation in birth rate and variation in terms of that diffusion coefficient and the initial number of people there. But you'll notice over time we get this sort of imbalance I described. We have, on average, a larger birth rate than we do the death rate, and this partly reflects the fact that the draw for the birth rate is from a truncated normal distribution. If it were normal, it would be pretty close to the mean, but we've truncated on the lower side to have a minimum of 0. And as a result, it tends to bias it a bit larger. And there's a holdout cell here, but as you can see, it's getting darker. It's building up, and if we go and we look at population, we're going to be having larger and larger populations growing here. So, ladies and gentlemen, we're going to stop this. We need some way to keep this system in balance. We've got our desired heterogeneity in terms of births, but we need some way to keep this system, ladies and gentlemen, in balance. Okay. So what I'm going to do here is I'm going to introduce another global parameter. We're going to introduce density dependence. So right now we have birth rate being set, and it's the same no matter what density of animals we have. No matter what the patch population is, we have the same birth rate applying. Now this is unrealistic for many reasons. Often organisms depend on eating some resources there locally, be they vegetable matter, algae, or what have you, or other animals. And the more animals we have, often the less of that food supply there is, and therefore the lower the birth rate. In addition, often nesting sites are limited, and the larger the population, the worse the average nesting site will be. The good ones are taken, and other animals have to take less good ones. Therefore, they're more vulnerable to predation or to environmental risks of exposure, what have you, and therefore the birth rate tends to be lower. Lots of reasons why birth rate is unlikely to be independent of patch population, but right now in the model it is, and we're going to change that. Okay, so what we're going to put in place here in main is we're going to put in place a parameter that's going to reflect the density dependence of birth rate. So we're going to go drag in a parameter, ladies and gentlemen, that is called density coefficient for birth. Okay, and it's going to be a double precision value, and its value will be 0.02. And basically what this will be is a to multiply by the number of organisms to adjust the birth rate. So the larger the number of organisms, the smaller our birth rate will be. And there'll be a bit of math associated with that, which we've seen before in this boot camp, in the form of a logistic relation, which basically reflects the fact as the number of organisms goes up, the birth rate goes down, and it does so according to a logistics curve. Okay, so we inserted this into main, density coefficient for birth. And now, we're actually, ladies and gentlemen, going to rename birth rate at a patch level to instead be called low density birth rate. So this will imply the fact that when we specify it, we're specifying a birth rate that obtains, that applies when the density is low. Now, we started to type this, and to spare ourselves from errors, it'd be nice if we follow these directions here. We press Control Enter to perform refactoring. So I'm going to press Control Enter, and it's complaining, okay, you can't replace it, so we're going to have to do it manually. Sometimes that happens if there's existing formulas in place for it. So I'm going to say low density birth rate, and then we're going to build, and we're going to see what we have to change. I know we have to change this thing for sure. Okay, but it's going to tell us where we have to go to change things. So low density birth rate, and let's go see what things depend on it. So it's building, and yes, it says it's unhappy. And the two things that it's unhappy about, indeed, both relate to here. First of all, it's saying that it doesn't know where birth rate is. Second of all, it's saying there's a link here, but it's not using it. Well, we'll fix both of those. Now we got to change this to low density birth rate. Okay, there we go. Okay, it's a happy camper. Let's go to main now, and let's go up to patches. And you will find that now this formula we gave previously for something called birth rate has been translated for this low density birth rate. It realized they're the same thing. So we have this low density birth rate. But so far we haven't changed the mathematics of it, just the name. To change the mathematics, ladies and gentlemen, we need to insert a dynamic variable. Okay, and this dynamic variable we'll call, without privileging the name, birth rate multiplier for density. Okay, so basically this is going to be a multiplier times the low density birth rate for that, and then we're going to add another one called effective birth rate. Okay, effective. Okay, and ladies and gentlemen, this should go here. Okay, so now rather than this directly impacting births, it's going to impact effective rate. Oh, come on, get over there. Okay, it's gonna affect the effect rate. Okay, so I'm gonna drag in another link here, and it's gonna come from here, and it's going to go over this. There we go. And specifically, this effective birth rate is going to be given as a dynamic variable, so we just specify its formula: low density birth rate times birth rate multiplier for density. Okay, so it's this guy is the multiplication of this one and this one. So we have this low density one, and then we're going to have some coefficient, as it were, some multiplier that's going to reflect effects of density, and it's going to make it lower than this one. Okay, now this birth rate multiplier from density, based on its name, you know it's got to depend on the density of this patch, the number of organisms in it. So it needs to depend, ladies and gentlemen, on this patch population here. Okay, so we're going to drag in a link from patch population to birth rate multiplier for density. Okay, and here we go. Here we have a patch population, and it's going to influence this birth rate multiplier for density. But what is the form? And okay, so that's good. What is the formula going to be for this? It's going to depend on this patch population. It's also going to depend, ladies and gentlemen, on this density coefficient for birth. Okay, so we're going to go put that into place here. That density coefficient for birth lives in Maine. It's a shared value among all the patches, and this has got to depend on both. And unfortunately, AnyLogic doesn't have a really nice way of shadowing something that lives at a different class like that. Okay, so we're going to put in a formula here, and then I'm going to explain it. The formula is going to be 2.0 times a formula that itself going to vary from 0 to 0.5, depending on the value of patch population. So it's going to be 1.0 minus 1.0 minus a legit curve. Okay, you can put a parentheses or something too. It's a classic logistics function, the one I'm going to be drawing right now, or that I'm working on right now, and it's in this form: 1.0 divided by 1.0 plus some exponent, and the exponent is going to be minus main dot, and it's this density coefficient for birth, in other words this guy right here, times, ladies and gentlemen, times this patch population. Okay, and I just got to balance the parentheses here, so this one goes with that one goes with that one, and then there's one more to reflect the fact that we have this one minus. Now, this is computing a value, so we don't need any semicolon. It's not telling it to do something. It's giving a formula to complete a value. We don't need a semicolon. Okay, now let me build this and make sure I haven't made a silly mistake. Okay, it's saying an error. We're going to see if that nope, it completed success. But not expected. Let's see where that is. Okay. Yeah, right there. We haven't completed. we'll come back to this. Let's finish that guy just to make sure there's no errors. So we need a formula in short, or we need a link in short betweenst this effective birth rate and birth rates here. Okay, so we're going to drag that in just like that and put it to births. Okay, here we go. Hey, come on, get over there. Okay, so for births, instead of being low density birth rate times mature, instead we're going to have the effective birth rate times mature. Okay, it's going to be this guy times mature. This guy, the effective birth rate, taking into account not only the birth rate at low densities, but also this multiplier effect coming from densities. The fact that our births tend to be lower at higher densities. Okay, so I built it. It's a happy camper. Ladies and gentlemen, let's go look at this guy here. Okay, the formula that we put in here, it's somewhat of a big formula, so I'd like to reason it through. Let's put it up on the big screen. Okay, boom. Okay, now it wraps in an unfortunate way. Okay, simple point to prevent it from wrapping. To explain it, I'm just going to say pop here. Okay, or patch pop. There we go. Okay, so let's reason about this formula. This formula, I would argue, goes from 0 when patch population is very large to when patch population is 0, when there's no other when it's very, very low, approaches 0, the birth rate is at its highest value, and this multiplier will be at its value of 1. So we'll have to be able to realize the maximum birth rate at low density. In other words, this low density birth rate when it's low density. So let's reason about this thing, okay? So let's consider the fact when patch pop is 0. When we have no other organisms around, or very, very small, this thing times this, if patch pop is 0, this thing times this will be 0. X to the minus 0 is x to the 0, which is 1. So x to the 0 is 1. And so we're going to have in this denominator 1 plus 1, which is going to be 2. So this is going to be, when patch pop equals 0. So when we have very low density, what birth rate is going to apply there? Obviously, to give birth, there have to be some organisms around, but what birth rate will apply around when patch pop is approximately 0? Well, it will be, as I said, this thing is 0, so this thing times that thing will be 0, so x to the 0. So this is going to have, you're going to have, just copying this down, and I'll leave out the zeros, the 1.0, just put in the part in front of the decimal point. So we get 1 over 1 plus, and I argued that this is 0, so this times that is 0, so x to that is, x to the 0 is 1. So we get this, which equals 2 times 1 minus 0.5, right? Or, excuse me. Yes. Oh, okay. Yes, that's exactly right. Which is equal to 2 times 0.5, which is equal to 1, which is what we want it to be. We want this whole thing to be 1 while when it's at low density. In other words, when the number of animals are in that patch are very, very small or 0, we want the low density birth rate to be used. So we want a multiplier here, which is 1. So when we multiply them, this will be 1, and we'll be using the low density birth rate. By contrast, let's consider when patch population is very large. Okay, or we could say as patch pop goes to infinity, right? What obtains here? Okay, so I would argue this thing gets very large. Hence, this thing times that thing gets very large. So we have x, but that's e to the minus some very, very large thing. which is the same as 1 over e to the very large thing, which is an even bigger thing in the denominator. Hence, it approaches 0. So x both minus something very large is going to be very close to 0. And the bigger patch prop gets, the closer and closer be to 0. Go to 0 very quickly. Okay, or you could think of it as 1 over this big thing, e to this big thing here, and that 1 over this huge number, and it's going to 0 as patch prop grows. Okay, so we're going to have here 2 times 1 minus 1 divided by 1 plus, and this, I argued, goes to 0. E to the minus this thing as patch prop gets large. Goes quickly to 0, in fact. So we have this, right, which is equal to, 1 minus 1, which is equal to 2 times 0, which is equal to 0. In other words, as patch prop goes to infinity, as patch prop becomes very large, this coefficient, the whole darn thing, approaches 0, which is what we want. We want the effective birth rate to go to 0 as we get a huge number of organisms in this population. So as patch population goes to infinity, effective birth rate should go to 0. Fewer and fewer nesting sites are available, less and less food to sustain these organisms, worse problems with exposure to predation or what have you, less good environmental conditions, effective birth rate goes to 0, and as a result we'll get less births. Okay, so that was our birth rate multiplier for density, and I'll again put it up on the big screen. You can watch it from up on the screen if you're trying to enter this. Okay, so that, ladies and gentlemen, is our density dependent relationship on births. Okay, ladies and gentlemen, let us say this, and let's run this model. So just have variability in rates between the different cells. We guaranteed that earlier. And then we're going to have, ladies and gentlemen, not only a variability in birth rates between cells in this low density birth rate, but we're going to have a density dependence, which makes sure that even if the system's out of whack in terms of its basal birth rate, in terms of its birth rate at low densities, the system can only grow so much in terms of its patch population before stabilizing. And the lower the patch population will get, the more efficient birth will be, and therefore it will tend to sustain itself. Sorry, we had one other thing we wanted to do, for the mean birth rate, I would like to use the value mean birth rate. I would like to use the value 0.2, and we should probably call this now mean low density rate. Standard deviation in birth rate, to reflect its real use, ladies and gentlemen, we should call it standard deviation low density. Low density rate. This is just sort of good naming in order to reflect the fact that we have what we're actually specifying, low density birth rate. Okay, so here we go, standard deviation low density birth rate. Okay, and let's make sure, I'm going to move this guy over a bit so we have space for this one, and let's make sure that the patches all refer to the appropriate names here. Okay, so they're going to be unhappy, so we need to change it low density birth rate here, and we probably could have done the refactoring, control enter there to rename this. So we've gone and changed these names to reflect their intention, how they're actually used. So for the patches, ladies and gentlemen, we need to go actually refer to them properly. So not just standard deviation birth rate, but the change name standard deviation low density birth rate, similarly for mean low density birth rate. Okay, let's build this model, make sure it's happy. Here it is, it's happy. You notice the simulation is happily accommodated the new names. And ladies and gentlemen, for this mean low density birth rate, make sure it is 0.12. Okay, and the low density standard deviation birth rate should be 0.05. Okay, so let's run it, ladies and gentlemen. Let's run this thing and let's see what we get. So we should be able to run it, and we see some variability initially. And over time, ladies and gentlemen, there's starts to be certain cells, presumably cells with higher amounts of high birth rates, effective birth rates, which are darker. Let's go amongst these. Okay, this is a low density birth rate, 0.117. Let's go to this one, 0.128. 0.179, 0.155. But you'll notice that when you multiply, then the effective birth rate is actually lower. Okay, but we have this variability being extended. So a given high density area, one with a high birth rate, it leads to migration to neighboring areas, and one with low birth rate suck things in from neighboring areas, but there's density dependence. There's something which limits the higher this is, as we've said. Let's go down to one of these. The higher this value is, the more the birth rate multiplier. So the higher the patch population, the smaller the birth rate multiplier will be, and therefore it will suppress the low density birth rate. The large patch population will limit the number of births, the effective birth rate. So here we have a birth rate multiplier 0.859. Let's look at this one. Here 0.785. Here 0.587. It's almost half the there's enough of a population. It's almost half the effective birth rate. So the effective birth rate is far less than the low density one. Whereas in something with a very low number of individuals, here this is, it's approaching that. And if we found one with a very low number of individuals, indeed, like this guy here, we'll see a birth rate multiplied 0.981, and we have an effective birth rate very close to low density. There's lots of good nesting sites, etc. There is the idea. Okay, now just one final thing to do. Let's go to main, and ladies and gentlemen, we are going to go. Okay, we want in main to set the neighborhood type. Instead of to be dependent on 4 neighbors, make it 8 neighbors. We'll transparently handle this model, ladies and gentlemen. You may remember that it's going to be handling it transparently because we have in patch a bit of mechanism that's going to get the neighboring patches at the start, and now it's just going to be getting the neighboring patches in the 8 areas instead of the other areas. Okay, so here, ladies and gentlemen, we can use this. We can just switch in main, which sets the environment for that population, scroll down to the space and network area, and set it to be a neighborhood type of 8 neighbors. And so now again we can run it. Okay, and here we go. We can run it, and we will see, ladies and gentlemen, patches emerging that are presumably associated with high birth rates. But now we're going to actually see broader patterns of diffusion around these, reflecting the fact that instead of just having in the 4 cardinal directions, north, south, east, west, instead we're going to have neighbors in all 8 directions. So north, south, east, west to be sure, but also northeast, southeast, southwest, and northwest. And I won't bore you, but if you run this model for a few minutes, you'll see is patterns where there be continued variability. After all, there is differences in birth rates that are quite salient, but there will also be sort of fringes around these points where you'll get migration into those areas, so it'll tend to be somewhat higher around these sources of migration. You could see one developing out there, and you can see some developing in this area here as well. So, ladies and gentlemen, running a model out like this, you'll start to see patches coming up, which will have some variability, but also some regularities and some continuity, as it were. Okay, so after a few minutes, it looks something like this. Okay, so thank you very much. It's a pleasure to be able to share with you this advance. We have now a rather more robust and heterogeneous and textured patch model associated with diffusion of organisms through geographically mapped patches. Okay, so I hope that's been useful, and hope that you'll find the model of benefit for your interests. Thanks very much.